Well, it's here. It's been a long time coming, but I finally got around to publishing this video. Today, we'll be discussing Theo's video on why you shouldn't learn Rust. But before we get into that, I want to thank Bash Bunny for actually pushing me to finish this video. I originally announced this back in December, but a combination of work, winter break, and procrastination got in my way. So if you end up liking this video, I'd appreciate a sub, and I bet she would too. Anyway, let's get back to it. If you haven't seen Theo's video, I recommend giving it a watch first. The link should be in the description. The too long didn't watch is this. Rust is great for a lot of the reasons that languages like JavaScript are not, but Rust has faults too. And Theo believes that Rust's faults make it less useful as a language in situations where the code might change frequently, whereas languages like TypeScript offer a more compelling developer experience in those situations. I believe there's a lot of confusion around Rust and what actually makes it great. Given Rust's learning curve, it's hard to experience what makes Rust great with only a few weeks or even months with the language, though we'll get to that part in a bit. Without further ado, let's get started.
Things that make Rust great. First and foremost, performance. The performance in Rust is nuts. The safety and reliability are also really important. Rust is meant to write code that is maintainable for a long time and also can run for a long time. And as a result, Rust is very scalable, both in runtime and in architecture. Specifically, like team code base size. So your app can get huge and still run well and have a lot of people contributing to it. And the code itself, as long as you're not telling Rust's rules to be, or as long as you're not ignoring all Rust's rules and honoring the compiler and borrow checker, your code can run super reliably for long sessions too.
While I agree with all the points on the list, it makes me a bit sad to see performance listed first and foremost here. Let me explain. A lot of people know Rust for its performance, and I'm aware it's one of the more heavily advertised benefits of the language. But I think, in general, many seasoned Rust programmers would tell you it's the strong type system, reliability, or the maintainability of Rust that actually stands out. There are situations where the performance characteristics of a language can be the factor deciding whether or not your team ends up using that language. But a vast majority of the time, that decision is not heavily influenced by performance. For that reason, it makes me kind of sad that developers are often under the impression that the benefits of Rust can be summed up to
blazingly fast
and memory safe. It makes it easy for folks to dismiss Rust if the benefits of the language are misunderstood. Then, the drawbacks, like steep learning curve, don't really seem worth it in contrast to alternatives like Python or Golang. It's a bit like dismissing Java because write once, run anywhere isn't worth working in a verbose language. You're not even considering how amazing Java's debugging and profiling tools are, the interop with other JVM languages, the expansive ecosystem, and how fast it can be when it's JITted. Don't get me wrong, I think this list is good, and as you'll see, Theo's final point on scale is effectively the thesis of this video. However, my concern is performance is listed first. To me, this is a subtle indication that the real benefits of the language have not really been experienced yet. Part of that is due to how difficult the learning curve of Rust is. It can take a while before you're comfortable and productive in the language, where these other less obvious qualities start to shine. Unfortunately, because of this, we don't often hear of organizations picking up Rust unless if it's in performance critical scenarios. There are a few choosing Rust for its stability and maintainability, but it'll take time for the industry to adopt it further for those reasons. Oh, and one last point. You can't ignore all of Rust's rules. I assume Theo is talking about unsafe here. That's a common misconception. Unsafe does not turn off the borrow checker. It has a specific set of things that you're allowed to do inside of unsafe that you can't do outside of it. It just so happens that these are enough to violate memory safety, which is why we have the keyword.
Let's also talk about things that make JavaScript bad. The things that make JavaScript bad are performance, safety. Is reliability really a problem in JavaScript? Memory leaks, runtime slowness, not very scalable. Big code bases are like whack-a-mole. Might notice something here. There's a lot of overlap between the things that make Rust great and the things that JavaScript is bad at. However, a lot of these things have been addressed in the recent years. Performance, V8 is killing it. Yeah, like performance in JavaScript has been consistently.
As I said before, I don't think performance is the most interesting aspect of a language, and it is not often the highest priority item when deciding what language to use. But Theo is right. JavaScript has been getting much better with all the crazy work that the V8 team has done. They should be proud, and I'm excited to see how they'll continue to push it further.
Safety, obviously, TypeScript has helped us a ton here. It's not memory safety, but it is runtime safety, and it makes your code much less likely to break in runtime because of something you weren't expecting. Somebody else also.
TypeScript is a massive improvement over just plain JavaScript. In fact, a study was done that analyzed the effectiveness of using TypeScript to catch real-world bugs. The study found that approximately 15% of these bugs would have been caught by just simply adding types. The authors also note that this is measured against bugs that are public, actually checked in and visible to other developers. The public bugs are more likely to be errors understanding the specification because they're usually tested and reviewed, and in the case of field bugs, deployed. Thus, this experiment under-approximates the static type system's positive impact on software quality. Basically what they're saying is that the number of bugs that would have been caught would be higher if they weren't just testing against public bugs. Another study found that static type systems were not found to have that much an effect on writing simple software from scratch, but there was significant improvement when writing non-trivial software from scratch as well as debugging tasks. To that end, TypeScript developers get to benefit from the power of a static type system. This means faster development on complex systems, less bugs in source code, and faster debugging when bugs do arise. One other aspect that Theo doesn't talk about here is that because TypeScript supports gradual typing, rolling out TypeScript to an existing JavaScript codebase is relatively simple. It's even easier than Rust's story around migrating an existing C and C++ codebase. Though, one issue to keep in mind is that TypeScript's type system is unsound. This means that despite the types you've written into your code, it's possible that TypeScript will say that something type checks, but it definitely doesn't. This is a known issue to Microsoft, who, due to TypeScript being built on JavaScript, are unable to fix many of the soundness holes in the language. In fact, they've declared it not a goal of the language to patch those. Many type systems are actually unsound, but I was surprised to see how trivial it was to write unsound TypeScript. The unsoundness holes appear trivial enough that you should expect to run into them every so often as bugs. That being said, this doesn't mean that TypeScript isn't worth using. It'll stop many more bugs with types than bugs that you'll be tripped up on by TypeScript's type system. Overall, this is a very strong argument in favor of web and software safety.
Memory leaks and runtime slowness. Do you know what helps with these? Lambda. Serverless. The fun of serverless is if you have a memory leak, it doesn't matter because the instance dies, it gets remade. You don't have to worry if your runtime is temporary and you're not maintaining a very long process. Which also,
to be honest, this sounds like a modern day version of the old missiles are garbage collection story. For those unfamiliar, this story was pulled from an email where the author recounts a memory that they had working with a customer. The customer was building onboard software for missiles. They helped the customer analyze their code and determine that there was a number of memory leaks. After telling the customer about their findings, the customer recounted, "Of course it leaks." It turns out that the customer had already calculated the amount of memory that the application would leak in the longest possible flight and then doubled that amount. Then they made sure that the hardware had that much memory on board. This way, the missile would still be able to reach its target and then, in the ultimate form of garbage collection, explode. It's a fun story about how not all memory leaks are bad, and we can see a similar mentality taken here. Use serverless if your memory leaks. It'll blow up at the end of 15 minutes anyway, but this has a ton of costs, some more fiscally obvious than others. For one, serverless is often very expensive compared to more persistent counterparts. If you have a high traffic API, serverless costs can get very expensive very fast. I used to work at a company that was investigating using Lambda for data ingest. The cost per hour was absolutely astronomical compared to EC2 or long-running Fargate instances. The other cost you incur is on performance. While cold starts have gotten better in the past few years, serverless technology still suffers from the cold start problem. For those unaware, cold starts happen when no instance of your code is actively running. If something hits your API gateway and it triggers your Lambda, it can take upwards of a second or two before your code starts running. If your plan to deal with Lambda's pricey nature was to run a 128 megabit or 256 megabit instance, you'll be looking at anywhere from 750 millisecond to 1200 millisecond cold start latencies. For infrequently used APIs, where cost is low, this has a non-negligible impact on tail latencies and latency metrics. But maybe the occasional blip in your API is totally okay. But leaking memory in a Lambda is a really bad idea for reliability. Obviously, if you run out of memory while a request is being processed, it's understandable why the current request may fail. However, the way that serverless systems typically work, and often to JavaScript's benefit performance-wise, is that the Lambda will stick around for a short period of time, typically up to 15 minutes. This limited persistence allows systems like V8 or a JVM to have an opportunity to JIT the bytecode and avoid cold starts. However, if you run out of memory on a Lambda, the Lambda is likely to return process exited before completing a request. In fact, one developer had to come up with a workaround which involved pushing up an empty Lambda configuration change to AWS. This would shut down the Lambdas, allowing them to cold start again, but that brings us back to the latency problem, except this time the cold starts are much more exaggerated. Lambda memory issues are common enough that Tableau, the analytics software company, released a blog post about a year ago detailing an issue with V8's GC. When used in Lambda environments, V8's more comprehensive GC pass mark and sweep will only run when the stale memory is at least 512 megabytes. For those keeping track at home, that's about 4 times the size of Lambda by default. It's not as simple as making your Lambdas 512 megabytes in size either. That's supposed to be stale memory. Your Lambda needs to be larger. This means that if you're dealing with particularly egregious memory leaks, you'll need to increase your Lambda to at least 768 megabytes or more just to properly diagnose issues and maybe evade out-of-memory conditions. Is there ever a case where memory leaks are okay? What about the story about the missile manufacturer? Clearly some cases are okay, right? Well, not exactly. In fact, these days, a lot of safety critical systems, which are systems in which their failure can result in the loss of human life, have to follow very strict guidelines and regulations on how they are written. For example, the Software Considerations in Airborne Systems and Equipment Certification, aka DO178C, necessitates the verification of the absence of storage exhaustion behaviors. Memory leaks. Oftentimes, software written for these systems are just statically allocated and analyzed ahead of time. Of course, that has more to do with systems that can literally kill you if they run out of memory. This is very unlike the software that most of us work on day to day. While the impact of memory leaks in more typical applications are often limited to just short-term outages, serverless and Lambda especially are not cost-effective, reliable solutions to memory leaks, especially under any sort of appreciable load. In my opinion, it's a band-aid fix and an abuse of the technology.
But this is why we have to talk about less great Rust stuff. DX in common tools is not great. Specifically, my VS Code experience was really rough.
My understanding is that Theo had a less than stellar time while writing Rust with VS Code. It's unfortunate to hear that there were problems with the Rust analyzer, whether it was taking too long to provide inlay hints, suggestions, or not showing errors as they were written. I actually found this open GitHub issue discussing some of these problems on the Rust Analyzer repo pretty disheartening. As for me, I've been a JetBrains fan for many years at this point, so I naturally use CLine, JetBrains C++ Rust IDE. JetBrains has implemented their own Rust LSP that works a fair bit better. It's every bit as capable as RA and available in CLine as well as IntelliJ. However, I understand not everyone likes JetBrains IDEs. They're heavy and their plugin ecosystem is not as extensive as VS Code. I know that VS Code has taken the developer community by storm, and we should honestly be investing more in improving that experience. What I take issue with is the generalization of the developer experience across Rust tooling. In contrast to pretty much every other language I've worked in, Rust got dependencies right. In my last 5 years writing Rust, I've run into 2 dependency conflicts. 2! However, my short professional experience with TypeScript was much worse in contrast. It was pretty common to find that by updating some dependencies, a few other dependencies broke. Fixing builds was tedious, and it felt like a game of whack-a-mole. It's not just the JavaScript TypeScript landscape either. Java dependencies are a nightmare to declare. Gradle and Maven are objectively worse experiences than Rust's cargo.toml. Speaking of cargo, there's no need to learn a bunch of different tools to package your code, to publish it, test it, etc. You can do all of that within Cargo. You want to build your code? Cargo build. Want to add a dependency? Cargo add. Want to create a project? Cargo new. Generate your documentation? Cargo doc. Which leads me to the documentation side of things. Rust's first-class doc comments make it easy as hell to create amazing API documentation, with working code samples, introdoc links, and so much more. Cargo doc generates HTML out of the public API of our packages and the dependencies of our packages. And yes, TypeScript has tsdoc, but we don't need authors to document their code. The public items will still show up in the generated documentation, and given how strong that static typing for Rust is, it's a lot more obvious how to use it. If something is still confusing, we can just click to view the source code of that thing in the browser or in your IDE. It's incredible. Let's say that we want to be a good author. Well, we can include code samples in our documentation, and Cargo can validate that our code samples will still compile even after we've made changes or refactored. This way, your documentation doesn't become stale and useless. I've never been a big fan of tests, but this is one of the few times I've been personally excited by them. Certainly been bitten by out-of-date code samples. There's so much more to the developer tooling experience, but in short, I believe Theo encountered an unfortunate, thorny aspect to the developer experience at the moment. An important one, but one that's not representative of the whole. Rust isn't the most beloved language 7 years in the running without the tooling being incredibly easy and simple to use.
Top of that, learning curve is steep. A deep understanding of memory is kind of necessary. Like suddenly pointers and all that stuff starts to matter again.
Oh yeah, Rust's learning curve is a problem. I think a big part of this is that it introduces some fundamentally brand new ideas, in the computer science sense, to many people for the first time. Move semantics change the way you think about problems and how to write your code. This means it's not as simple as learning some new syntax and maybe a bit of syntactic sugar, but you need to relearn how to code with Rust. For other folks, they come from languages like Python, where types are merely a suggestion. So having to pick up static typing and figure out all this ownership and borrowing nonsense can be quite difficult. That's why it's hard. What is less true, though, is needing a deep understanding of memory. As you learn more and more Rust, you'll inevitably pick up on those topics. However, you can definitely get to the point where you can write web apps or be generally productive, and you'll almost certainly not need to know if your data is on the stack or the heap. It'll help, but not required. And unless if you're building your own high-performance data structures or you're doing embedded programming, you're certainly not going to be using pointers. As a criticism for the Rust community though, please stop forcing these topics down the throats of those reading your tutorials. It's unnecessary and only makes learning Rust harder and scarier to approach.
Generally, more code to write per feature, and
that's totally valid. Rust can be pretty verbose, and that's especially true when you start using trait bounds for added safety. Though something that might be a bit underappreciated here is Rust's macro system. Rust's macro system allows us to easily abstract away repetitive code. And you can even define your own domain-specific languages, or DSLs, which can feel very natural given the kind of work that you might be doing. A great example of how powerful this system is Diesel, Rust's safe and extensible ORM. And while Rust may typically take more code to write the same logic, typing speed is usually not the bottleneck for development. Throughout my career at least, most of my time was spent reading and writing docs, chasing down bugs, dealing with flaky tests, and designing, not implementing features. So to that end, I don't really see this as a strong reason to not consider Rust.
And developers who are experienced in Rust are more expensive.
I wish this were more true than it is. While Rust developers aren't cheap, they're actually compensated pretty similarly to Go developers, which is, a much easier language with a more mature job market. A subtle contributing factor, though, is that junior Rust dev jobs aren't really a thing. These days, when jobs are specifically hiring Rust developers, they're typically looking for senior developers. That's partly because the kinds of systems that we're seeing being built in Rust require more technical expertise to work on. I think it's also partly because Rust is a relatively new language for the industry with a high learning curve. Therefore, we don't really have as many established practices, interview loops, and success stories that other technologies have had yet. This isn't something that's exclusive to Rust though. In fact, a similar thing happened to Golang around 8 or 9 years ago. Back then, most positions asking for Golang experience were for intermediate to senior level devs. They were also pretty exclusively doing systems level programming. So the whole build a web app or microservice in Golang is a bit more of a recent phenomenon. I don't think that we'll be seeing a massive influx of junior Rust developers in the future, but I certainly anticipate as more people learn the language and more places adopt Rust, that the job market will open up a bit and compensation to sit probably around where Golang sits today and change depending on the field.
The problem with this is, what happens if the feature you made in Rust is a bad feature? Not because the code is bad. The code can be incredible, and it often will be. But the actual thing we built with that code ends up being bad. Then the developers who built on Rust are much less willing to throw that thing away. The problem with each line of code being more expensive isn't just that it costs more to make the code, because theoretically, if I'm a good enough developer, I can go just as fast in Rust as you can in JavaScript. It still was more work to do it, fundamentally, and no Rust developer is going to disagree with that. It is more work to build in Rust than it is to build in TypeScript.
We can summarize what Theo said into 3 parts. 1. It is more work to write Rust, even if you are similarly productive to someone using JavaScript. 2. Not all features are good, and developers should be willing to throw away the bad ones. And 3. Rust developers worked harder to write that feature, and therefore are less willing to throw it away. Is Rust more work to write? Well, I'd say it depends. Oftentimes the answer is not really. Just like any language, after you get over the initial learning curve, much of the code you end up writing is pretty trivial and obvious. You won't find that the Rust borrow checker is getting in your way, and you'll be making pretty steady progress on whatever you're writing. That's especially true if I'm writing brand new code. I'm not fixing a bug or updating an existing feature in this case. When I am, Rust feels like a dream. I mean, think about that paper from earlier. Static type systems help make debugging and maintaining code easier, and a vast majority of software development is not writing brand new features and throwing away code. In fact, over 80% of developers work at companies with at least 500 employees, and 67% have at least 1,000. At these sizes, a lot of work is done dealing with legacy systems, tech debt, existing feature work. Also, companies at these sizes typically have like TPMs and product managers, UX specialists, and analysts, and their job is that they help identify the needs of customers, and they do a lot of that work up front to validate features and products before any code is written. Some of you may have even received an email before from like Google or another large organization where they offered like a $50 or $100 gift card for participating in a user study. Those are what I'm talking about. Those user studies occasionally use low code or no code methods of having customers try and test features for viability. That way they don't require investing, otherwise valuable dev time to implement something that won't work. But what happens if after all this work, the product still flops? Well, with products, sometimes that product is left to hang around, and other times they'll be sunset after a while, though that process usually takes months or years. It's not an overnight decision. When it comes to features, after organizations grow to like a certain size, they're pretty rarely thrown away, usually just kind of deprecated or left to sit there. I believe Theo values the ability to get something done as quick as possible and be able to toss it at a moment's notice because he's a startup founder. Startups reward the ability to quickly iterate and toss ideas that aren't working. The code doesn't have to look good, and some bugs are okay. What's important is user feedback and iteration on the product. I mean, if you don't achieve product market fit, your business will go under. It doesn't matter that your code was this bug-free, elegant, type-safe solution if you can't pay your employees. And from this perspective, I totally understand where Theo is coming from. However, a vast majority of us will not be working for small startups where these values are rewarded. Many of us have or will work for older companies with many employees and teams, piling tech debt and scale. Those businesses will have folks dedicated to working with users ahead of time to figure out what customer needs are.
But generally speaking, I think that there's a spectrum of how often is this run, and then like how often does this change. And generally speaking, there's a slope like this. It's actually more like this, of how often code runs versus how often it actually changes. Where when you first write code, you're going to be changing the shit out of that code all of the time. But as things stabilize and you get more customers, this curve starts to happen. And there are points on this line where different languages make more and less sense. I'd say above this line, TS, TypeScript type stuff makes a lot of sense. Below this line, Golang is a pretty solid option. And then you hit a point where your code is running a lot and it's not changing anymore or as often anymore. And at that point, something like Rust really starts to make sense. But
in my opinion, the problem with this diagram is that it measures the wrong things. As I said before, startups need to be able to iterate or they'll die. There's little chance that the very first thing they build is what ends up taking off. Take Slack, for instance. They were a gaming company before they pivoted. At these early stages, it's all right to have a buggy product as long as you can learn more about what your customer needs are and iterate. So at this stage, it makes sense to use whatever gets the next version out quickest. After your business starts to take off though, and your product is successful, your customer base is large and growing, then considerations like scale begin to matter a lot more. Delivering a stable, reliable experience to your existing customers becomes more and more important. Security concerns begin to grow too. You're more of a target, and the impact of a breach, or at least the bad press, is more painful. Maintainability is more top of mind within those dev teams too. It's at this stage that a lot more organizations begin to consider languages like Golang and Rust. It's not about how frequently the code is changing. It's about the flexibility afforded by the success of the organization. A business that's 3 months away from bankruptcy shouldn't care about scalability, stability, or correctness. That's not going to matter in 3 months. However, an already successful, established business is looking to stay on top. Being able to iterate is important, but how a larger organization iterates looks very different from a startup. So the next concern is keeping the existing clients happy, and no one wants to use a buggy service that's constantly down. Not to mention, at that scale, organizations are a lot more concerned with being able to actually iterate with so many different teams having their hands in every other code base. And keep in mind, rewrites are expensive. When your 5-person startup makes that decision to write your core web service in Ruby, you might find that 5 or 10 years down the line, working in that service is dreadful. Iteration in that code base becomes slow and precarious. Your worst bugs end up hiding the most legacy parts of that code, and all of the microservices supporting it are built in something more maintainable with a stronger type system. If this is starting to sound familiar, it probably should. So many companies end up following this model. Dropbox did. Dropbox's core web service is written in a monstrous pile of Python and on an outdated, almost unrecognizable web framework. Thank goodness Dropbox hired the guy that made Python and funded all this work to give Python a type checker, since working in that code base was not a fun time. However, many of the newer services at Dropbox were being written in Golang and occasionally in Rust. But this is if everything works out, and 90% of startups fail, so it's not really worth solving for problems 10 years down the line when all you have is 12 months of runway. So where does Rust fit into all this? Well, generally speaking, languages like Rust are probably best suited at more established organizations that can be more methodical about the software they're building. It's not about how often that new code is changing. It's about the stage of life that organization is in and the level of support that organization is able to afford. Rust can do a lot of good for an established code base. Facebook is using Rust for all of their CLI tooling. Dropbox uses Rust to ensure that your files are stored correctly, and Cloudflare is practically fronting the entire web with Rust. And while organizations are often trying Rust out in performance-sensitive situations, they're learning after the fact that Rust has so much more to offer. And statistically, most of us are probably going to end up working at a larger organization at some point in our career. I recommend making sure Rust is in your tool belt before that happens. Thanks for watching. Do you agree with my perspective? Does Rust sound like a language that you might consider learning? Let me know in the comments. And if you haven't seen Theo's video, give it a watch. He has a few additional things to say about Rust that I didn't have time to address in this video. Plus, he actually uploads more frequently. Anyway, thank you for watching, and until next time.